Imagine a big maze. You spend your life running through it, left, right, forward, nowhere. You start marking the walls, desperately trying to memorize the paths. You think you are getting close, but then they drop a machine into the maze with you. A robot. It's faster, it doesn't sleep. It was trained on the maps before you even open your eyes. If it beats you, and it will, you starve. No food, no water, no future. Most people just run faster. They watch another 40-hour tutorial trying to outrun the machine. They are going to die inside that maze. But what if you stopped? What if you did the one thing they never expected? What if you climbed the wall? From up here, the maze is small. From up here, you see the logic. You see the patterns. You don't fear the machine. You command it. You stop being a runner and you become the architect itself. 30 facts to climb the wall, one fact at a time. Let's go. Facts 1 to 10. How computers actually work. 1. Computer science is not really about computers. It's about managing complexity. The computer is just a tool we use to do that. 2. Every technology ever built, every language, every framework, every database, every cloud platform is doing one of 5 things: storing something, moving something, transforming something, making a decision, or coordinating between multiple things, doing the first 4 at the same time. That's the whole map. Store, move, transform, decide, coordinate. 3. At the bottom of everything is a transistor, a tiny switch, on or off, 1 or 0. Your entire laptop is a few billion of these switches firing in a coordinated sequence. 4. A CPU takes those switches and turns them into instructions. Fetch an instruction, decode it, execute it. That loop runs billions of times per second. That's all a processor is doing. 5. RAM is your computer's short-term memory. Fast to access, but the moment you cut the power, it's gone. Everything your running programs need right now lives here. 6. Your disk is long-term memory. Slower to access, but permanent. When you save a file, it moves from RAM to disk. When you open it again, it comes back. 7. The operating system sits between your software and your hardware. When your browser wants to save a file or send a network request, it asks the OS. The OS talks to the hardware. Your programs never touch the hardware directly. 8. A process is just a program that is running. It has its own private memory space. It can't touch another process's memory. That separation is intentional. It stops one crashing program from taking everything else down with it. 9. A thread is a worker inside a process. One process can run multiple threads at the same time. They share memory, which makes them fast, and also makes them dangerous if they are not managed carefully. 10. Every layer of software that sits above the hardware is an abstraction. It hides complexity. But every abstraction has a cost. The further you are from the middle, the harder it is to understand why something is slow or broken. Facts 11 to 20. How the parts connect. 11. Memory isn't flat, there is a hierarchy. Registers inside the CPU are the fastest and the smallest. Then cache, then RAM, then disk, then the network. Every step down is dramatically slower. Most performance problems are actually a data allocation problem. The right data isn't in the right place fast enough. 12. The stack and the heap are 2 regions of memory. The stack handles itself, memory gets allocated and freed automatically as functions run. The heap is where you manually request memory for things that need to live longer. Forget to free heap memory and it builds up forever. That's a memory leak. 13. An algorithm's efficiency is measured by how it scales, not how fast it runs today. Big O notations answers one question. As your input gets bigger, how much more work does your program do? The wrong algorithm on a small dataset feels fine. 1. On a million records, it can destroy you. 14. A database index is a separate structure built specifically to make finding records fast. Without one, every search scans every row. With one, it jumps straight to the answer. The trade-off is simple. Indexes made reads faster and writes slightly slower. 15. A network packet is a chunk of data with a destination address attached. Every router it passes through makes one simple decision. Which direction gets this closer to where it's going? That's it. The whole internet is built on that one repeated decision. 16. TCP is a reliable delivery contract between two machines. It guarantees your data arrives in order without corruption. UDP skips the contract. It just fires data and doesn't check if it arrived. TCP for your bank transfers. UDP for your video calls where a dropped frame is fine. 17. DNS is what translates a domain name into an IP address. DNS gives back a number. Your computer connects to that number. Every website visit starts with this lookup. It's the phone book the whole internet depends on. 18. An API is a contract between two programs. It defines what you can ask for and what you get back. What's happening behind it is irrelevant to you as the caller. That's the point. You don't need to know how something works internally to use it correctly. 19. Concurrency is handling multiple things at once. Parallelism is literally doing multiple things at the exact same instant. Concurrency is about a structure. Parallelism is about hardware. Most bugs that only appear in production are concurrency bugs. Two things trying to change the same data at the same time. 20. A cache stores the result of something expensive so you don't have to do it again. Your CPU has one. Your browser has one. Big platforms run entire caching layers. The hard problem isn't caching. It's knowing when your cache data is no longer accurate. That's one of the genuinely hard problems in this field. Facts 21 to 30. What the senior engineers know. 21. The two hardest problems in computer science are cache invalidation and naming things. That's a real saying and it is serious. Knowing when to throw away a cached value is a problem that has caused real outages in real companies. 22. Every system that writes data has to answer this question. What happens if the power cuts out mid-write? The answer most databases use is a write-ahead lock. You record your intention before you act. If you crash, you recover from the log. Simple idea, critical in practice. 23. The cap theorem says a distributed system, one running across multiple machines, can only fully guarantee two of three things. Consistency, meaning everyone sees the same data. Availability, meaning the system always responds. Partition tolerance, meaning it keeps working even if machines lose contact. You pick two, every distributed database is a version of that choice. 24. A race condition is when your program's behavior depends on the timing of events you cannot control. It works perfectly in testing. It silently breaks in production when two users hit the same function at the exact same millisecond. These are some of the hardest bugs to find. 25. Latency is how long one thing takes. Throughput is how many things you can handle per second. They sound related, but they pull in opposite directions. Optimizing one often hurts the other. Knowing which one your system actually needs is an architectural decision, not a technical one. 26. A load balancer sits in front of your servers and distributes incoming traffic across all of them. When one server goes down, the load balancer stops sending it traffic. This single pattern is foundation of how large systems stay up when individual machines fail. 27. Eventual consistency means your system will reach the correct state, just not instantly. In a distributed system, when you write data to one machine, the other takes time to sync. During that window, different users can see different versions of the same data. Some products accept this, others can't afford to. 28. Microservices are not a technical decision, they are an organizational one. You split a system into independent services so separate teams can build and deploy without waiting on each other. The code doesn't get simpler. The coordination just moves from code to the network between services. 29. Observability means being able to understand what's happening inside your system from the outside. Logs tell you what happened. Metrics tell you how it's performing. Traces tell you where time went across multiple services. Without all three, you are guessing when things go wrong. 30. Every architecture is a set of trade-offs. Speed versus cost. Consistency versus availability. Simplicity versus flexibility. There is no perfect system. There is only the system that makes the right sacrifices for the specific problem it's solving. The senior engineer's job knowing which trade-off to make and being honest about what it costs. On the screen is the CS survival sheet. Don't just stare at it, use it. Drop a screenshot of this into any AI and give it the exact prompt in the description. The AI will give you a perfect study note that is understandable. Then you ask it questions, tear the code apart, learn and build. Keep a notebook on your desk and memorize only the logic and the patterns. Leave the syntax to the machines. The job crisis is moving opportunities away from the coders. If you are willing to put in the effort, you will have a chance to be a survivor in a matrix. Right now is your chance to choose a pill.